Go.
Math is an intimidating and unapproachable subject for many people in our modern day life. But I'm here to tell you that through gaining an understanding and an appreciation for math, it can be useful for gaining an understanding of many other things in our world. Even the things that appear as far away from math and science as possible, such as creative outlets. This is my TED Talk on chaos in music. Chaos is a field within mathematics that looks at underlying patterns in systems that seem completely random or unpredictable. A system in this context is a group of things that interact and evolve with each other according to some set of rules. For example, picture waves crashing on a beach, and try to imagine a piece of foam or a particle floating around. It seems almost impossible to predict where that particle of water could be in the next 5 minutes. But if you think about it, everything that affects that water particle is something defined. From the attraction between particles, forces of gravity from the Earth and from the Moon, or from conservation of momentum between collisions. And so on and so on. So if you think about it, if someone knew everything affecting a system, they could theoretically come up with some crazy complex mathematical way to completely predict the movement of water. Turbulent water flow is just one example of a chaotic system. Weather patterns, traffic, and pendulums also are chaotic. This video shows two pendulums where they're spaced just a little bit apart from each other. And as you'll notice that in the beginning, they follow some sort of pattern, but eventually diverge and take their own paths. This is a good example of chaos, as you can see how even if we completely understood the movement of one of the pendulums, just by altering that pendulum just a little bit, it suddenly becomes unpredictable. I propose that chaos can be used to explain many things in our modern world, including musical structure. Chord progression, time signature, keys, and crazy chord choices are just some of the infinite levels of structure that appear within our music. That brings me to my research question. How can ideas of chaos theory relate to the evolution of musical structures and the creation of music? The first connection between chaos and music I want to talk about is the structure formed through interacting instruments and players in free jazz. If you have heard of free jazz before, or have heard about it from a friend, you might think that it's just improv where the players can do whatever they want with no rules whatsoever, free to play whatever chords, whatever notes, and whatever pattern. In fact, my main inspiration for this project came from an argument I had with a friend where I was trying to convince him that free jazz was actually good and that he just didn't understand. But he refused to believe me until we sat down in a dark room and listened to a 30-minute free jazz song. Afterwards, he came out enlightened, a new man, with a new appreciation for free jazz. My research suggests that free jazz does have structure, and it can be explained through a chaos theory concept called phase spaces. Phase spaces are built off an idea called Taken's theorem, which suggests that one variable in a system contains information about the others. For example, think of a group chat where you can only see one person's replies. Even if the whole conversation was happening and you didn't see every text, just from that one person's replies, you could get an idea of what the conversation was about. For a more visual understanding, look at this graph where we see the populations of sheep, wolf, and grass. You can kind of understand intuitively how these variables interact with each other. As grass population grows, the sheep have more to eat and their population grows. The wolves have more to eat, so their population grows. But the sheep eat the wolves eat the sheep, so their population shrinks, and so on and so on. This is the same graph graphed in 3D. I want you to pay attention to the shape that it forms. What Taken's theory suggests is that we could isolate the variables. These are the variables graphed in 3D, but on their own. What Taken's theory says is that by just looking at a single one of these, we have enough information to reconstruct the original series. The resultant prediction of what the series would look like is called a phase space in the phase space reconstruction. But what does this have to do with free jazz? Imagine the players in a free jazz band as interacting variables, where their instruments are colliding and interacting with each other, where from one interaction of the instruments, we can make a prediction of what could happen next in the song. That's what researcher David Borgo suggests is going on. This is a free jazz song called Hues of Melanin by the Sam Rivers Trio. I want you to pay attention to the horn player and the bass player. Here in that moment, you can see as Sam Rivers ascends on the horn, the bass player comes and meets them at the same pitch. I want to mention that this is improv and that was not planned. What Borgo suggests is that interaction and the following interaction were not just coincidence, and that they could be explained by what happened previously. In other words, the information from that interaction of the bass player and the horn player aligning on the same note is what foretold the preceding action of the drums picking up tempo, the bass picking up tempo, and the horns having this moment of craziness. In terms of chaos, in terms of Taken, that means that without knowing what the drummer was playing, we could reconstruct a phase space off of what he could be playing. This complexity in free jazz structure, it was what makes free jazz so complex. And the higher structure that chaos emulates suggests that free jazz could be modeled as a chaotic system and better be understood in that sense. The next connection between free jazz, or between music and chaos that I want to talk about is the structure and the patterns that notes form within songs. This graph shows three interacting equations that originally were meant to emulate weather patterns. As the dot goes around, you'll notice how it follows some sort of pattern. Eventually, the dot splits into three, meant to showcase what would happen if three different dots were started at slightly different times in the graph. The dots seem to follow each other around for a little bit, but eventually diverge and take their own paths within the pattern. This is called sensitivity to initial conditions, where we see how just by slightly altering the starting spot, new patterns and paths form. This is another characteristic of chaos. Also notice how the dots never line up back with a starting point, meaning that although we see a pattern forming, it is not a repeatable pattern. This general pattern that the dots are tracing out is called an attractor, in this case, the Lorentz attractor. In broader chaos terms, an attractor is the general shape that a chaotic system follows over time. Attractors could also be compared to fractals, which is a shape that exhibits an infinite amount of detail. That means that as we zoom into a fractal, we could zoom into the edge forever and forever, finding new and also repeated patterns. This is a zoomed in section of the Mandelbrot fractal. Another good example of this is the logistic map, where it has characteristics of bifurcation, where as we follow the path along, it splits into pairs and continues to split into pairs and pairs as it goes on. This factor of self-repetitiveness is a characteristic seen in many fractals. This is a zoomed in section of the logistic map where we see that similar pattern just continuing on. This structure is also present in the music that we listen to, such as in Ludwig van Beethoven's Fifth Symphony. Here we hear that beginning three notes be repeated and built off of each other as the song continues. Another good example is the Oscar Peterson's trio ending at the Come Dance With Me. See with that, the three-note pattern again repeating and building off into the end structure. This suggests that note structure can form some sort of complexity that can be described by chaos, and how understanding those structures helps us understand the complexity of the music. The final connection between music and chaos I want to talk about is predictability. In music, we also often use the terms consonance and dissonance to describe the music. Simply put, consonance is groups of notes or chords that sound good together, and dissonance is groups of notes or chords that sound bad together, or some measure of unpleasant. The defining factor of consonance or dissonance simply comes from the ratio between the notes. For example, take the 440 Hz A note. Multiplied by that frequency by 2, we get an 880 Hz A note an octave higher. That 2 is the ratio, where we see that more complex ratios compared to 2 over 1, 3 over 2, 4 over 3, which are all consonant, and the more complex ratios like 16 over 15, 45 over 32, produce more complex ratios and therefore more dissonant sounds. So why would a composer use any dissonance at all if it sounds some measure of unpleasant? Well, our brains can naturally guess what note would sound good next. So imagine a succession of notes. Your brain knows what note could sound the best afterwards. So if you think about a composer, if they only used the next note that would sound the best, it would sound some measure of predictable or boring to the listener. So that's why a good composer utilizes a balance of consonant and dissonance to take the listener on some sort of journey. For example, take the chord progression. See there how I use a balance of consonant and dissonance chords to take you, the listener, on some sort of listening journey. But what if predictability could be some form of measurable inside music? For example, take the composers Maria von Weber and Wolfgang Amadeus Mozart. And imagine after hearing some section of music, the audience could guess what the next section would look like. And by taking the surprises that the audience would hear in that section, dividing it by the number of sections, you could get some sort of surprise factor in that music. Jonathan Salter takes a more mathematical approach to this, where he does find, in fact, that Weber is naturally more predictable in his composition compared to Mozart. Chaos can also be considered in terms of predictability, where a chaotic system is somewhat on the verge between predictable and unpredictable, where in terms of music that could look like a predictable song being less chaotic and an unpredictable song being more chaotic. Jonathan Salter also brings up the argument that perhaps why Mozart is thought of as such more of a high regard than Weber in musical history is because of his use of complexity in his composing. Perhaps that our brains crave that complexity and unpredictability in our music, and because of that, we tend to stay away from music that is naturally more predictable and boring to our minds. In other words, Weber wrote music that made sense, while Mozart wrote music that made you make sense of it. To sum up, this evidence proposes the idea that humans' brains naturally enjoy less predictable, more chaotic music compared to more predictable, less chaotic music. And that through understanding the role of predictability in chaos, the listener gains an understanding of what makes a musical composition more complex in its balance of consonance and dissonance. But why does any of this matter? Who cares? My research suggests that through gaining an understanding of chaos, you can better analyze and understand the structures that lie within our music. That includes the underlying structures in free jazz, how melody note traces can exhibit fractal characteristics, and how complexity arises from a balance of predictability and music. It also supports the idea of gaining a deeper appreciation for music. Meaning that you should all now love free jazz. A further implication with my research suggests that if we could possibly understand and mathematically define the topics within music that we like with chaos, perhaps AI could have a better time reconstructing those patterns and creating music that could possibly match that of human composition. But I think the most beautiful takeaway here is that creativity from either jazz or any other art form doesn't spring out of nowhere. It comes from structure, from rules, from constraints. And that through understanding chaos theory, it shows us that what seems free or random could also hide patterns and structure within it. And learning to see these patterns could help us understand the art a little more. Thank you.